And I would suggest then we go to the next presentation by Robert, Sophie, and Marike on modular transformation of Java exceptions, modular errors. And Robert is here, I think also the others, but Robert will take the questions after the presentation. So feel free to post them during the talk. Okay, please play the video.
Welcome to my presentation titled Modular Transformation of Java Exceptions Modular Errors. The paper was written by me, Sophie Lathouwers, and Marike Huisman. So let's get started. So first I will give you a brief introduction into the concepts that you need to follow along in this presentation. Then we will discuss the exceptions modular error semantics. Then we will discuss how we encode Java and exceptions into a backend language with only goto. And finally, we discuss how the approach was evaluated, and we conclude. So first, introduction. We discussed deductive verification, deductive verifier capabilities, and abrupt termination. So what is deductive verification? Deductive verification is a formal method that can ensure that the system follows a specification. So what this means is that a system is proven correct with regard to a deductive system of rules, which means that if you deductively verify a system, you follow a system of rules to show that the system actually follows a specification. Now, this is based on mathematical foundations, so you can be sure that once a proof is found, then that the system is actually correct. However, the user does not see any of this. The user only reads and writes the specification and, of course, the system. So what does this look like? On the left-hand side, we have the user, and user writes the program and the specification, or maybe the specification is provided by yet another user. But in any case, the program and the specification are combined and they are handed to the verifier. The verifier then performs executes an algorithm to figure out, using deductive verification, if the program actually follows the specification. And then there can be three results. Either the verifier says correct, which means the program follows the specification. The verifier says wrong, which means the program does not follow the specification, and maybe the verifier can provide a counterexample. Or the verifier says I don't know, which means the search simply timed out. So what does this look like in practice? So here you see a Java method that computes the maximum of two numbers, except when one of the numbers is negative, then an arithmetic exception is thrown. And we also, in blue, in the comments, we also provide a specification. And any comment that begins with an @ sign by the verifier is interpreted as a verification annotation. So on line 1, you can see the post condition, which says that the return value actually has to be equal to the actual maximum. And then on line 2, there's an exceptional post condition, which states a fact that has to be true when an exception is thrown. Now, one deductive verifier that we will focus on for this presentation is Faircore. Faircore is a deductive verifier for concurrent languages, and it uses separation logic to guarantee absence of data races and guarantee functional correctness. It accepts 4 input languages, namely OpenCL, OpenMP, PVL, and Java. And the way it works is that Faircore reads an input program in one of these 4 languages, then converts it into its internal format, call, and then applies several transformations on the tree to simplify it down to a level where the internal representation, can be easily converted into Silver, which is the input language of Viper. Viper is the backend of Faircore and can do more elaborate verification reasoning on the input. Then Viper will return the results, and then Faircore will translate the results back to the level of the input. Of course, deductive verifiers, they seem like a very nice tool to use. You can write specification and check if your code follows it. So why are these deductive verifiers not used everywhere? Well, we have 3 hypotheses for this. The first is that using a deductive verifier requires an upfront investment. So you might have to write a big specification of your code, and that can be a lot of effort. but we won't be focusing on this answer. The second answer can be capacity of tools. So it might take a very long time before a verifier can prove that your system actually adheres to the specification. However, we are also not going to look at this answer. The third answer is that deductive verifiers do not support the languages that they can analyze fully. And this is the answer that we will be looking at in this presentation, and also how we will improve the situation. So for this work, we have looked at several verifiers that exist in the same niche as Faircore. And what you can see is above the center line, we have two verifiers, Nagini and Gillian.js. And they actually support both exceptions and separation logic. So if you have a program that uses concurrency in those languages, you can actually verify them in a pretty complete subset of the language. However, for Java, the situation is not so good. There's no verifier that supports both concurrency through separation logic and that also supports exceptions. So what we are trying to do in this work is try to add this extra row to the table, to have a verifier there that supports concurrency through separation logic and also can analyze exceptions. Now, as a bit more background to exceptions, we have to discuss abrupt termination. Abrupt termination is a grouping term for when a statement terminates earlier than normally expected. Then, when this happens, control flow is redirected to any program point, which means abrupt termination is not linear or structured control flow, but it's actually a separate category of control flow. Some examples of abrupt termination are the throw statements, return, break, and continue statements, but also labeled break and continue, which give you almost arbitrary control over where you want the control flow to go. So here's an example of abrupt termination using throw and finally. The dotted line indicates what linear control flow is, and you can see it proceeds linearly through the program. And then the thick arrow shows you what abrupt termination is. And you can see that as soon as the throw statement is encountered, abrupt termination takes over and redirects control flow to the nearest finally. Now you can imagine that in this simple example it's quite clear where to go, but for more complicated programs this control flow might become quite complex and tangled. So now let's discuss the exceptions modular error semantics. So to dive into why we need this, we first need to discuss the distinction of errors and sources of errors. Then we will discuss the ideal semantics and why the ideal semantics is less useful. And finally, we will discuss the optimal and usable semantics that we ended up implementing in Faircore. So, errors versus sources of errors. In Java, there are quite a few error types, such as the ones listed here. But it is important to note that these types are just object types. You could use them in your program for entirely different purposes. They have no semantic meaning besides their name and maybe whatever is stated in the documentation. For example, the VM might decide to throw an internal error if a bug happens, but this doesn't mean. But you could also use the internal error type as a sort of container for your data. This is not really useful, but you could do this. There's nothing preventing you from doing this. Now, then there are also error sources. Error sources are the events that cause the error types to be thrown. So, for example, if a bug occurs in the VM, then the internal error type is thrown. Or if the system runs out of memory when allocating, then the out-of-memory type is thrown. It is important to note that these can be separate. So the error source of running out of memory doesn't really imply that is not exactly the same thing as the out-of-memory error type. So when error sources occur, error types are thrown. It's important to note that there is a mapping between these, but they are not one-to-one. So one cannot simply get rid of the one by just excluding the other. This is a complicated mapping. So just to give you an example of how this works, here I have a simple function that concatenates two strings and adds a semicolon to both strings. And finally, when the strings are concatenated, it returns a string on line 7. Now, this is a typical Java program, or at least it's somewhat idiomatic, even though it's not very useful. And there are already 4 places where an out-of-memory error could be thrown. So first on line 2, when allocating a string builder, Then on line 4, there are 2 occasions where the out-of-memory error could be thrown, namely when concatenating the strings, a new string has to be allocated, and when appending the string, of course, maybe the buffer needs to be grown. Same for line 5, and for line 7 as well, when the final string needs to be created, also new memory needs to be allocated. So even though one wouldn't expect there to be any problems with this piece of code, there are only at least 4 locations where you might get an exception, even if you write just idiomatic Java code. Now, what would be the ideal semantics that we want to implement in the verifier? The ideal static analysis tool would implement the Java language specification. So it would just implement everything that is described in the document to the letter. This maximizes the chance of capturing the behavior of a bug and hence being able to guarantee that if a verifier proves the program correct, then the behaviors it will exhibit will actually also be correct. However, we think the ideal semantics would not be useful to implement in the verifier, namely for 2 reasons. First is the reason of induced annotation overhead in user code. And second, there will be the problem of the runtime dependencies. So as we shown earlier, it is hard to write Java methods that do not allocate. From this we conclude it is likely that most Java methods allocate at least indirectly. And from that we conclude that most Java methods will at least need the following contract in ideal semantics. So the contract that we show below here in blue is a exceptional post condition which states if an out-of-memory error is thrown, the post condition is true holds, which means the method can just throw an out-of-memory exception and there will be no guarantees. So it's very likely that if you just write idiomatic Java code, you will need at least this contract everywhere, which makes a verifier very unusable because you have to write a lot of meaningless annotations. Now, the problem is not so much that implementing these error sources in Faircore is hard, because that's the job of a verification engineer. And once these have been implemented in the verifier, you can use them. But the point is that this will generate a lot of meaningless annotations that the user will have to write. Whereas we would like there to be only exceptional post conditions if you're actually dealing with exceptions and not just generate exceptional post conditions everywhere, because that will make them meaningless. The second problem is that of runtime dependency. Well, what we mean with this is that error sources may depend on the runtime environment. For example, the class format error might be thrown if improperly formatted code is loaded. Now, this is not something you can exclude at compile time, because you might have a library that you get from a server at runtime. And then, this is impossible to prevent. Well, of course, it's not impossible. You can impose a lot of runtime requirements. So you might say, the class path has to look like this with exactly these files on it, and we only support this VM version. And maybe that way you can get away with a lot of exceptions. You can prevent a lot of exceptions. However, this is quite non-standard. So this is not something we want to impose yet upon the user. Maybe future work can resolve this. So from these 2 problems, we conclude that the ideal semantics is not a useful guideline to implement. And instead, we need to look at something that more accurately represents how we actually use Java. So now we will discuss the optimal usable semantics that we settled on, that we think is the best option. So we define an optimal usable semantics, and we call it exceptions modular errors. And specifically, it is a subset of Java semantics where exceptions can only come from the throw statement and method calls. Now, what does that mean in practice? This means that all exceptions that occur in a program come from a throw statement or method calls, and they are handled in either a catch clause or they are indicated in a throws clause. So specifically, if you annotate a method with a throws clause, you can say this exception can escape without us handling it. Additionally, there are also several problematic errors that Faircore will prevent by default, because these are part of the functional correctness guarantee that we give. Now, why do we think this is a good idea? First, it reduces the annotation burden. Specifically, the user will never have to annotate for exceptions like internal error or out-of-memory error, as these depend on the runtime environment anyway. And additionally, you're not really expected to recover from them, so the annotations would not be very useful. Furthermore, in practice, the throw and throws, so the throw statement and the throws clause are the only considerate sources anyway. If a programmer has a problem with exceptions, they don't first check if the VM has a bug. They don't start reading the VM source code. What they do is they track down where the exception originates from, which is almost always a throw statement, and they start figuring out why the throw statement was triggered. And finally, if there were ever a situation where a user would like to use or would like to keep track of the out-of-memory error, then user can opt in to that behavior by annotating methods with throws clauses that say that an out-of-memory error might be thrown, and a Faircore can analyze the program to ensure that that exception is handled. And this is why it's so important to separate the errors and the error sources. If we would have just excluded the error types, then the user wouldn't have been able to opt in to this behavior. Whereas if we just exclude error sources, then the user can always add the error types when it is necessary. So now we briefly discuss how we encode Java exceptions. Why is this important? Well, first, if we consider the case of encoding exceptions into goto when not considering finally, this is no problem. The plain behavior, as described in the JLS, is that whenever a break is encountered or while is exited, continue jumps back to the beginning of a while loop, return exits the method, and a throw jumps to the nearest catch clause. This is straightforward. However, when the finally clause is encountered, an ambiguity might arise. So in this example, the break statement on line 5 wants to exit from the inner while loop, and the break statement on line 7 wants to exit from the outer while loop. Now the problem is that both these break statements will redirect control flow to the finally clause. So they will kind of coalesce there, and after the finally clause, these two control flows have to split up again. So there's a natural ambiguity that occurs there that you cannot resolve without remembering what statements you originated from. So when you encode a language from exceptions to a language with only goto, you have to make this ambiguity explicit somehow. Now there are 3 options for this, 2 of which we have seen in earlier work, and the third one is somewhat novel. So the first one is Inlining Approach. It's seen in practice often. It's intuitive and it works well, but you risk blowup because finally clauses are inlined recursively. Then there's the control flow flags approach, which basically is a way of, or it solves the problem of the blowup by setting a flag when control flow changes, and then whenever an ambiguity arises, you can inspect this flag to see what control flow needs to happen. But it's harder to implement because there are more variables to manage. We didn't like this. And the third way to solve this is to implement the control flow and finally by converting to exceptions first, and I will show how that works now. So what to do after a finally? It's not immediately clear. Do you have to exit the try statement that the finally belongs to? Do you exit a while loop further down in the program? Or do you exit the entire method? So you can only know this if you somehow resolve this ambiguity. But there is a simplification we can do. So let's say we only consider exceptional control flow, then this question becomes a lot simpler. If there's currently no exception being thrown, then we can just exit the try statement because we know, where the current control flow is regular. Otherwise, an exception is being thrown, and then we know, okay, we need to go to the next finally or catch clause. Now, this makes the control flow decision a lot simpler because it's a lot more homogeneous, and you only need to know about the next catch or finally clause. So the insight here is that if you manage to, if you can get to a situation where you can only consider exceptions, encoding finally is straightforward. And the strategy we take here is first we convert all abrupt termination to exceptions, and then we convert exceptions to goto. With the consequence that the transformation becomes more modular. You only have to know what the next catch or finally clause is at the end of the finally clause. So this simplifies code generation. The only requirement for this is that you first convert break, return, or continue to throw, but we argue this is straightforward, and for this we have an example. So here we show how to convert break to a throw statement, and this is done by replacing the break statement with a throw statement, and then surrounding the while loop with a try-catch clause. That way, the control flow that actually happens is preserved, but on the right it is implemented with exceptions, and on the left it's implemented with a primitive break statement. Now, to evaluate the approach, how do you evaluate such an approach? Well, the approach that we took was to first find out what the common exceptions patterns are that are used in commercial software, and then we tried to verify the patterns with Faircore. So we have surveyed 4 works, and we have arrived at the following patterns. On the left-hand side, you see all the language elements that occurred in catch clauses in practice. And on the right-hand side, you see all the language elements that occurred in finally clauses. And what we have done is for each of these elements, make a small test program and try to verify them with Faircore. So this is one example. This is the example that a stack trace is used in a catch clause. And we are very happy to conclude that Faircore can analyze all the examples that we listed in the table. So to discuss, there's one downside to exception modular errors, and that is that some bugs might be missed. So for example, we don't model failing on locations or stack overflow or other error sources. Now we think this is a beneficial trade-off because this is currently not possible anyway. Verifiers just do not mention these error sources at all. And it does give the user the ability to at least check if all throws and throw statements are handled correctly. So this is a beneficial trade-off. Now our method imposes several requirements on the backend. Specifically, goto needs to be supported, and also conditional permissions need to be possible. And finally, there are some performance concerns. Namely, we have seen that our method results in a bigger encoded output. There's more complex control flow, and there are more conditional permissions. However, we think this is also inherent to using exceptions because it just causes more complicated control flow. And these inflations are not problematic in practice. So while they increase the outputs are not necessarily that much more. They don't cause more problems than they already do. So to conclude, we have presented an approach for supporting exceptions in a deductive verifier by first converting control flow into exceptions and then converting exceptions into goto. With this, we implement a simplified exception semantics, exceptions modular errors. This reduces the annotation burden for the user at the cost of less precision. And finally, we've evaluated exceptions modular errors against common exception patterns, and we have concluded that it can handle the common exception patterns. So thank you very much for listening. That was the presentation.
Okay, thanks Robert for the nice presentation. I'm checking now if there's any question. Okay, so there's a question on the chat. Can you read it from there, Robert? Or should I? Ah, your mic is not working. Okay. You can type the answer if you want. Okay, I see. The focus is on deductive verification, right? Yeah, I have a question on this. I'm writing it now. Oh. So to continue the first question, how would you view the advantages, disadvantages compared to model checking, if you have an opinion on this? And then there is a question there are 2 questions in the chat as well. In the Q&A. I'm also writing a question here. I think your mic is working now.
Ah, okay. Is it not too loud or?
No, it's okay.
Okay. Yeah. So, well, to comment on a general question. In my experience in practice, the advantages of deductive verification are mostly that you can get stronger guarantees about or when you're dealing with infinite state. So if you have a problem that concerns a lot of integers in a big range, then deductive verification is very powerful. However, the upside of model checking in turn is that it is very clear and easier to use because it works with a lot more explicit state. So then you can, of course, you can deal with a lot of problems a lot more easily by just computing the whole state and checking if a certain property holds. And that is something that is really hard to do with deductive verification. So with deductive verification, you often have to provide lemmas to prove a certain goal. You never have to do that with model checking, which makes it a very productive tool, model checking.
Yeah, I think that's a clear answer. So then there's four questions in the Q&A, and I'm posting a question as well.
So the first question I see here, would it be correct to state that Faircore only supports controlled exceptions? Also, our try with resources and Java 8 Lambda streams construct supported. So I guess that's true. We only support controlled exceptions, but mostly Faircore also provides a way of dealing with unchecked exceptions in a structured way. Try with resources and lambdas and streams are not supported currently, maybe in the future, and I think try with resources might be supported soon, like within a year, maybe, but I can't give any guarantees. Have other users, programmers tried your tool? I know that there are several case studies have been done and are being done with Faircore. So in that sense, Faircore is being used. But specifically the code that I implemented to work with exceptions, I don't think it's very heavily used, but maybe, hopefully that will change in the future. It's always related to the point on annotations in the conclusion slides. Maybe you can clarify what you would like to know there. I don't really understand.
No, it was related, I think, to the previous question, whether other users tried your tool.
Okay. Well, if you want me to explain further, please don't hesitate to ask.
Alberto can intervene if he wants to.
Yeah.
But then there's a question by Enrico.
Yeah, would it be possible to elaborate a JUnit test suite that verifies to some extent equivalence between the original source and the transformed code? Sure, yeah, that would be possible. Faircore has a very layered architecture, so we have a lot of passes, and each pass produces an AST that is kind of executable. Sometimes it is not, but I guess after the transformations that I have implemented, the code should still be executable Java code. So you could actually do something like this to do some kind of runtime verification of the code that you transform internally. Yeah, that would be an interesting idea.
Okay, so then there's two more questions. So let's give preference to the questions from the audience. So Diego asks whether deductive verification can be used interactively, so while programming.
Yeah, I think it could be. Of course, it depends a lot on the tool. But if you look at tools such as Isabelle or Lean, these are very mathematical theorem provers. But these are you can use these interactively. So if you can adapt these to programming languages, then you can also do deductive verification interactively. And yeah, there's one verifier that's called Key, and that's kind of a deductive verifier that you can use interactively. So maybe you can look at that.
Yeah, that has strong tool support.
Yeah.
Okay, thanks for the answer. So then, well, I think we just have time also for my question. So basically, first of all, in the paper, I read that you are also planning to do an empirical, or at least planning, you say you might want to do an empirical study on this. I think this would be very worthwhile. So that's a remark rather than a question. And the question is about this go-to statement. So I was always taught that you should not use go-to statements, and you are introducing lots of go-to statements. So how come?
Yeah, so this is basically a constraint imposed upon us by the backend, which is Viper. And there, if you want to encode something else than a while or an if statement, you have to use goto. It's basically the building block. So the old adage that you're mentioning here, don't use goto, kind of, I think, doesn't apply to verification engineers. We need to encode the goto statement somehow, or at least we need to encode the control flow somehow. So, and then the only option is to use goto.
I see.
So yeah, but maybe we have to think harder about this, and maybe it's not so good idea.
It's a good thing. I learned something new. I thought they were to be avoided.
Yeah, well, they still are in practice.
Yeah, well, maybe the difference here is, of course, that you introduce them in a structured way, right? So
yeah, we try to.
If someone does this while programming, there's more risk to make errors, while you do this in an automatic deductive way. So, okay, well, I don't see any other questions. So let me thank you once again, Robert, for the nice presentation.
Yeah. Thanks for all the questions.
All these questions. And then we go to the last presentation of this session, which is the reason for the part after the end. So the session was on program safety and education. So we've seen something about the program safety. Now we'll hear something about the education. So the presentation is by Bernd Westphal on education and training in Fmics. So please start the video.
Welcome to the video presentation of our work on education and training in formal methods for industrial critical systems. In our work, we revisit the 2020 expert survey on formal methods from an education perspective. Most striking, next to the regular answers, are the experts' individual position statements, of which we have a somewhat broad selection here. Vital, fundamental above all, and at the same time a primary challenge, and insufficient. This does not paint the brightest picture and indicates that there are problems with Fmics education and training. The good news is that the survey, if read from the right perspective, already includes hints that allow us to better understand the problem and to work towards solutions. Two aspects are most important: the interpretation of the term formal methods that we worked with and the consideration of target roles, that is, the job descriptions that we are teaching for. With these two aspects, we will see that classical core formal methods education is a different thing than Fmics education. And this is a good observation because it allows us to get started talking about Fmics education, getting started to talk about its what, when, and how. And this is what this video is about: identify the problem, analyze the problem, and off to new grounds for the specific topic of Fmics education. Okay, now let's get started by taking one step back. What was this survey about? In 2020, Hubert, Maurice, and Jaco reported answers from 130 high-profile experts of the field to 30 questions on the past, present, and future of formal methods in research, industry, and education, as well as individual position statements, of which we have seen some before here on the top right. On the left-hand side is an excerpt from the conclusion. Note that of only 3 highlighted action points, the first one is again education and training. Now, we all know that we have about 20 years of conferences and workshops on formal methods teaching, all reporting one success after the other. We have plenty of articles on instructions on what to do and what not to do in formal methods teaching. We have an ever-increasing number of textbooks and even a teaching committee. Question: how can these two observations go together? The survey report's answer in a nutshell is as follows: formal methods teaching is teaching different content to different target people. Okay, now how is this the survey report's answer? To this end, let us get all quickly on the same page with the survey and the report. Here's an overview of the structure. We have an introduction, we have a section on methodology, and we have 5 sections on questions and answers. Here's research, industry, education, as promised in the abstract. And there's a conclusion of which we have seen a part before. Some questions and answers are more useful to understand the past and present, like missed opportunities over here or impact evaluation over there. And some already indicate solutions for the education challenge, most prominently the ones marked in blue, like here and here. But first steps first, to better understand the problem, these 3 sections turn out to be particularly useful. First of all, the terminology section, which discusses different interpretations of the term formal methods, which will help us to better understand the problem and to find solutions. In this section, the report firstly recalls 4 pretty much well-known interpretations of the term formal methods, going from right to left. We have a very broad interpretation: any use of mathematics in computer science, which would include linear algebra and computer graphics. a somewhat narrower one, the extensive theoretical one, which would exclude linear algebra but include formal languages, grammars, automata, and everything on top. These two are too broad for our purposes. On the left side, we have the lightweight and the heavyweight interpretation. Lightweight denotes language features like assertions and assertion checking, and heavyweight considers only those approaches that are fully mathematical and based on proofs. These, on the other hand, are too narrow for our purposes. And the report solution is in the middle, the modern inclusive interpretation of the term formal methods. It considers mathematics-based techniques for the specification, development, and verification of software and hardware systems. What does this mean? Well, suddenly we have included, for example, formal pattern languages in requirements engineering. We have all formal variants of class object diagrams, state charts, sequence diagrams included. So we have test generation from rigorous models and much, much more. And what this buys us is that this is today's industry critical system development. These examples have the chance to provide a strong common ground with, quotes, industry people, since many of the named examples are already in use in an informal or semi-formal fashion. Note that the interpretation is not as new as the term modern may suggest. The news and the contribution of the survey is to establish this interpretation for Fmics, to have about 130 experts agree on this interpretation, at least for the duration of answering the survey. Okay, so with this slide, we have the first aspect of content set. For the second aspect of target roles or people, let us take a look into the survey report again. Question 5.5 is about limiting factors for a wider adoption of formal methods by industry. Note the wording. This is not phrased in terms of formal methods engineer over and over, but we have engineer, integration, developer, manager. And this is most probably not a coincidence, but tells us that today's formal methods for industrial critical systems has not only one role, like the formal methods engineer, but multiple different roles that have aspects of formal methods in their job description. The main role may in particular be mainstream software engineer. On the following slide, we have a first proposal on how a set of roles may be further characterized by looking into corresponding activities. So going from bottom to top, I see the well-known activities of developing and investigating formalisms, theories, and formal methods. This activity I call construct. One can also apply existing formal methods, create complex models, construct proofs, and so on. I call this activity conduct. Then here is a new one, which I call utilize. People who do this activity are driven by a product and have a clear understanding of the purposes of formal analysis and how to interpret analysis results in terms of the product domain. Note that utilize needs conduct, but it need not be the same person who is doing these works. In particular, in formal requirements engineering, we see a trend to consider conduct as a kind of service for utilize. Same in model-based design analysis. Then, to complete the picture, we have integrate and manage both with pretty canonical job descriptions. Now, the quotes proverbial academic doctor in formal methods can clearly be trained to do all these activities or even all. But the survey suggests that we should no longer have a one education fits all approach, and hence I propose to refine the formal methods engineer role into at least the following two. One that emphasizes conduct, that is the formal methods engineer as we know him or her, and one that emphasizes utilize with some overlap into integrate and manage. In other words, one that is concerned with the formalisms and the analysis, this is conduct, and one that is concerned with products and analysis outcomes, this is utilize. Now, if we put the interpretations of the term formal methods on one axis and activities on the other one, then I would locate classical core formal methods education around here, focusing on classical narrower interpretations and on people who construct or conduct. And right here, everything may be fine. The thing is that formal methods for industrial critical systems includes this larger area, a more inclusive interpretation, and people who are concerned with products. In other words, formal methods education is here, and Fmics education is more over here, different things. That is, now we have a location for the Fmics education challenge, say here. And now we can specifically discuss the what, the when, and the how. Interestingly, both moves together, so to inclusive and to utilize, open up a new design space. And I will present our corresponding design ideas and experiences in the remaining few minutes. Details are all in the paper. Okay, teach what, when, and how. The three tables here on the bottom right anticipate a bit of all three. The what is mostly in the light red areas here. For Fmics education, I propose to explicate and emphasize principles of formal methods and go for a good coverage of modern inclusive, but without heavyweight. This can be an elective extra course. I propose to emphasize reading and understanding formal models and analysis outcomes over writing formal models. Maybe have a mild form of writing in the form of modify or in form of well-chosen and well-designed small examples. Complex models can again go to an elective course. And I propose to approach formal methods from, say, the outside as a tool with an interface. That is, what are the inputs, what are the possible outcomes, and what do these outcomes tell us about the analyzed items. How to implement this interface, that's once again left to an elective specialization course. So here on the left is a proposal of a wording for 3 learning objectives that we work with. Let us only gloss over them. The wording and the thorough discussion are in the paper. The first one is related to the first and second box, so explicate the term formal methods and provide a good number of examples to substantiate or illustrate this interpretation. The second one relates to the middle and the right box. So focus on utilize, the product perspective. And the third one extends to the right box by suggesting to state and demonstrate which problems formal approaches are able to solve, and have this together with a discussion of advantages and disadvantages, not excluding the economic aspect. Good, that's the what. Now to the when. Where in the curriculum should we reach these learning objectives? Placing formal methods education in the curriculum has also been discussed for over 20 years. The schematic on the left is supposed to illustrate a more recent proposal. The big box is the whole study plan, say of a 3-year bachelor. Small boxes are courses in temporal order from top to bottom. And the arrows are like puts into perspective relation. So the proposed construction illustrated here is to have an introduction to software engineering as usual, have a compulsory course on formal methods somewhere between what we now call formal, modern, inclusive, and heavyweight, and revisit software engineering content from a formal perspective. Then maybe have a classical heavyweight formal methods course as we know them. For Fmics education, we propose to turn things around, to already have the modern inclusive interpretation integrated into an, quote, otherwise completely ordinary introduction to software engineering. With the following benefits, we avoid the extra work and overlaps that are needed to put formal methods into the engineering perspective afterwards. Second, we reach the mainstream software engineer who may not become a formal methods engineer, not even in utilize role, but may need to interact with some of those. And we have in scope, in a very natural way, the well-known motivation that system or software development should be proper engineering. For example, specifying requirements consistently can be important for well-known reasons. And this is why we discuss approaches and countermeasures against inconsistency on different levels, informal, semi-formal, and formal, at best with corresponding analysis tools and procedures. How these tools and procedures are constructed, this can be learned in an elective formal methods course. Okay, integrate modern inclusive formal methods into an introduction to software engineering is the proposal. But isn't this introductory course already brimful of material? Where do we put the new stuff? Interestingly, a solution is not that difficult if we take a closer look into the structure and content of contemporary software engineering courses and textbooks. If we zoom in a bit and assume, for example, 4 topic areas like requirements, design, testing, and so on, then the content per topic area is typically vocabulary and concepts, then lots of formalisms that are introduced in an at best semi-formal way, but often to the extent of quite some bit and detail, plus then a lengthy explanation of intuitive meanings. The thing is, this telling intuitive meaning stories is not quick, rather the opposite, it takes a lot of time. So if we remove bits and details and this telling intuitive meaning and stick to a proper sub-language instead, then we have plenty of time for formal methods for industrial critical systems. And with this construction, we can in particular achieve a pretty good coverage of the phases in the design lifecycle where the experts see formal methods most useful. In our case, for example, we cover formal requirements, model checking, building models. As said before, not so much doing this, but comprehending what it is about. Validation we have, code verification, and our students have at least heard of test case generation, code generation, runtime monitoring. Only maintaining consistency between models is left to later courses. So once again, what do we achieve here? Our goal is not to educate full-grown, for example, formal requirements engineers. Our goal is that the statements of the experts on the benefits of formal methods become plausible to participants of the course. That is, there are these kinds of problems in requirements engineering. The expert survey says that formal methods can help, and this is why this statement is plausible. This is how it principally looks, and this is how it looks when these formal methods help with requirements engineering. Thereby, we want to enable our course participants to connect to a broad set of future working environments by providing a good solid ground of principles and examples. This, to me, is Fmics education and training. For the conclusion, I want to close the circle to 2 findings from the survey, statements on the present and expectations on the future. So, Fmics education, as introduced here, remains challenging, but it need not be insufficient. Yet, the driving force may not be the classical formal methods education because of differences in content and target roles. The good thing is that the discussion of differences opens up new design spaces for courses. It is feasible to provide a good part of Fmics education in an otherwise completely ordinary introduction to software engineering, actually in a quite natural way. And this, in my strong opinion, is exactly where it belongs. Fmics education needs to be part of software and system engineering education. So in my opinion, students in industry alike should demand from their software engineering educators to get not particular methods in every bit in detail, but as a broad audience, principles and connection points. And this concludes my video. Thanks for tuning in.
Okay, thanks Bernd for this nice presentation. And thanks for picking up this survey, of course. So any questions? There are a few questions in the chat. Bernd, can you see them?
Yes, I see a few questions. I would change the order, so to say. So there's a second question that...
Change the order, yes.
The second question says, what is the difference between modern inclusive and heavyweight lightweight? And one example that I do not see included in heavyweight lightweight is, for example, these pattern languages that we see in formal requirements engineering. A second example is that a recent textbook starts on formal methods education starts with a sentence, UML is not a formal method or something. I don't have the exact quote. The thing is, UML class diagrams or a fragment thereof can be a formal software description language. And this one I would also not see included in the heavyweight, lightweight interpretation. Same as model-based testing, for example. So we get a broader scope of formal software description languages which have certain analysis about them that we can use as stepping stone connection point to industry people and prepare our students for this connection. The first question in the list is on reading, writing, modifying. Writing in the sense of creating a formal model of a system design. And this is a delicate didactical question, definitely. So if you, for example, visit the formal methods teaching workshop, you see that people report on the homework being modeling a whole sensor network system or a whole rocket control or cruise control system, and. So this needs a lot of background, a lot of description in order to build that model, and a lot of work. And I propose to more focus on principles rather than this huge extent which makes somebody already a half-baked formal methods engineer. And in my course, I'm working with smaller examples, so there is writing, but to see the power of formal analysis, I sometimes provide half-ready models where just some component needs to be added. Or I have a model with an error, and then modifying means understand the error and modify the model. Where this limit in effort that we put on writing is an unsolved didactical question to me, which needs further research. Then, what else do we have? Do we have this implemented? Yes, running since 2015, and the student feedback is, so two aspects are important to me, and these are, do people feel overstrained? So is it too much material per time? And the responses say clearly no. The figures are in papers that are referenced in the Fmics paper. And the second thing is workload. And we have the same picture there. So if we go to sub-languages, not the whole UML state chart with the formal semantics, but a useful small fragment of this language, which gives the idea of behavioral state-based modeling, we are well able to have a one semester course which is not overstraining in workload or level. Anything else? I think this have been the questions that I have seen. I would have one question to myself.
Yeah, there's a question by Anastasia still.
Anastasia, where are you?
If someone else that feels his or her question has not been answered properly, please speak up, because we're going in a shuffled order.
Yeah. So how do students react? And I mentioned tools. Yes, I have mentioned two tools, and actually I have not integrated neither Fred nor Han4. The thing is similar with this trade-off between reading, writing small, writing large models, is that in the kind of course that we are doing, we have to be careful about the effort and effect balance of learning a tool and achieving what we want. So requirements, we are doing paper and pencil. Class diagrams is too simple to learn a tool to do that. State-based state chart model checking for distributed systems, we have very good experience with UPAL, as many other educators, because this is far beyond paper and pencil to understand the power of formal analysis that you get. But what I would expect, so unfortunately I do not have a requirements engineering course. What I would expect is that I have a much faster start to get people into this business of Fred and Han4 and understanding the whole principle. What does it mean if Fred says there is an inconsistency? Well, the students, in my opinion, have to learn that there are two possible reasons. Either the requirements the customer thinks about are inconsistent, or I may have made a mistake in writing them down. This is what tool builders, very often this is core formal methods inside. And the outside, the interface view to me is, what are the consequences to the engineer if the tool says no, if the tool says contradiction, or the tool says violation of specification. Now, this is what I would put into focus for Fmics education, to connect these roles, core formal methods, then industry applications, and then the mainstream software engineer who still may need to interact with the people in the middle or here on my left.
The students, if I may interrupt, so the students of course have to realize that for many formal methods and like model checking tools, so the technique is as good as the model, right? So you have to make this clear to them.
Yes, that's the
abstraction is what they have to learn. And,
yes, and here, so the question to myself would be, how does this connect to yesterday's talk by Joe?
Yeah,
and actually, actually, I see my paper. This may be now overdoing things, but I see my paper as an educator's instruction write-up of Joe's talk. 3 messages are most important to me there. So one message is that things have changed in the last 10 years. So in my students, I have not seen what has in the past been called math phobia. I have not seen people coming with certain preconceptions about formal methods. I present the problem and I say this is a possible solution, and then we are doing engineering. I even have difficulties to approach, I once tried, to approach people with this myth-based approach. So some people say formal methods are like that, and it is not the case, it's like that. People have difficulties to follow me into these misconceptions. Second thing, it's not about selling formal methods, not at all. I really wonder whether a historian may find out how this selling came into the game of formal methods. What Joe says is it's about solutions. I have a certain requirements problem. I cannot manually check anymore if it is consistent, and there exist tools, and they may solve it, yes or no. And this is the story that I'm telling. And the third thing is use the right tool. So for Fmics education, I see it beneficial to give an overview over different approaches: textual, graphical, model checking, paper and pencil, structural behavior, requirements, models, code, verification, testing. So to have multiple bridgeheads or connection points so that people at least get an idea that there may exist the right tool for the right for the problem at hand.
But concerning the math phobia that you mentioned, so I think a lot is in the naming, right? I mean, you are claiming that so my claim would be that UML is not formal methods. You're saying it is. So and I understand both point of views, right? It's about what you name exactly. So I think
the thing is what you name exactly, and that's something that I also emphasize in the paper, that we need to prepare our today's student for meeting people like me and you who have seen 25 years of formal methods come and go. in this. So I'm strongly against not calling it formal methods because the term is in the world. You will meet it.
Yeah, of course.
And I want to prepare my students to clarify such discussions. And I think the students would have an easy time to follow me in saying UML has a formal, precise abstract syntax and a concrete syntax, and we can give it a formal semantics. And if we decide for one formal semantics, for example, the one from the OCL standard, then we have something that classifies as a modern, inclusive formal method.
Yeah.
And then we can prove things about structure.
Yeah, just to clarify, I'm not saying it's informal. I would call it semi-formal, but I mean, I just wanted to make the point that it's about the naming, right? So if you go to the more heavyweight formal methods, then you might meet this mathphobia reaction from students, right? So it's all about where do you draw the line?
Well, somehow I find it hard to see the semi if I have a precise meaning of a class diagram. A class diagram denotes a certain precisely defined mathematical structure. Et voila, we have a formal software description language. If I do not agree on that one, and I only stick with the pictures, then I'm informal, or at best semi-formal. But I can use class diagrams, sequence diagrams for formal reasoning if I understand these ingredients. I have a concrete syntax, I have an abstract syntax, I have a semantics, and then I may have analysis or reasoning procedures around it. And these concepts, I think, should be in the course. And we are reiterating this. Look, here's a class diagram, and it has a syntax, and this is the semantics. Look, here's a program, it has a syntax, and here's the semantics, and here's the reasoning for proving program correctness. You have to see this reoccurring pattern that all formal methods have in common. I think this is useful for students to better connect to future working environments.
I see your point. Okay. Nobody complained, so I think you answered all questions that were posed in the chat. If anyone still has a question for Bernd, then please speak up, raise your hand, or write the question. I don't see any questions. So yeah, thanks again then to you and to all the other two speakers, to all three speakers in this session. I think it was a very interesting session. I learned a lot, and well, we have used 15 minutes of the coffee break, but that leaves us still 15 minutes to actually get a coffee. And we'll be back, if you want, for the guest keynote talk, 3:45. And otherwise, the next Fmics session is at 5 o'clock. And please remember that there are different links, right? So you have to